Hi and good evening. My name is David Anderson, and today I'm going to show you how to correctly implement the idisposable interface. We're going to talk a little bit about the garbage collector and probably quite a bit of detail, managed memory, unmanaged memory, and how all of these things kind of tie together. This video is intended for those of you who have implemented idisposable. Maybe you know a little bit about the garbage collector. Maybe you've never implemented a finalizer, or you have and you're not sure if it's done correctly. Also, for those of you who are kind of have a fuzzy picture of what it all means, today I'm going to give you a crystal clear picture of how everything ties together and how it all works. So let's dive in a little bit. I've prepared. We're going to go through some PowerPoint slides, but I also have a program that we're going to demonstrate as well. I'm going to demonstrate to you a memory leak. I'm going to demonstrate to you various implementations of the dispose pattern and how those affect your program and the memory and things of that nature, and how it all interacts with garbage collection at the end of the day. So we're going to kind of go back and forth between the two. Before we dive into anything, though, we're going to do a very quick overview of memory and the dotnet framework and the runtime. And so the three main things that you need to understand at a very high level is that we're dealing with managed memory and unmanaged memory. Now, managed memory is allocated when basically you use the new keyword to create a new object. So if I say var x equals new my class, that is a managed object that memory was allocated for, and that's the kind of memory that the garbage collector can monitor and free up. Unmanaged memory will be native resources, either created through platform invoke is probably the most common way in a .NET application, or if you're using something like Marshall alloc H global to allocate memory, or if you're using unsafe code, that's another way that you can do that. Most of the APIs in the .NET framework use platform invoke to the Win32 APIs to create handles to native resources at some point in the program. Now, today we're going to be using a bitmap object for the demonstration because it's real easy to work with and demonstrate the behavior in your program. The garbage collector does not know how to free unmanaged memory. It doesn't monitor it. It is explicitly required by the developer to manage that in your application. So when we talk about automatic memory management in the runtime, we're explicitly talking about managed memory allocated by creating a new object. The third major construct is a finalizer, or in C#, there's a destructor syntax, which is tilde and then the name of the class. And that's just a sugary syntax for compiling down to a finalizer. But basically, a finalizer is a fallback mechanism if you do not wrap a disposable object in a using statement, or you don't call dispose directly. The finalizer is the last opportunity that the garbage collector gives you to do final cleanup of your native unmanaged resources. And we'll talk about that here in a few minutes, but we're going to go through a couple things. So I'm not going to educate you on all the different aspects of the garbage collector. That's a very detailed video for another date. The intent of this is to show you how to correctly implement idisposable so you get the correct behavior from the garbage collector. So this is all done, of course, through the idisposable interface, and you implement this interface when you know that you're dealing with unmanaged resources. If you have a class and you only have managed resources, there's no need to implement this interface because you have no unmanaged resources to clean up. How do you know if you have unmanaged resources? The easiest way to know is if your class has private fields that are storing objects that also implement idisposable. That's the most common thing that you'll have in your programs. The other way is if you yourself are using platform invoke, such as I can platform invoke into GDI plus.dll or GDI32.dll. I can platform invoke and create native bitmaps directly from my code. And in that case, I'm holding directly onto an unmanaged resource through maybe a handle of some kind that's returned back to me. But there are other ways to create or allocate native memory. You can do it through Marshall Allocate Global. You can do it through unsafe code as well. So let's kind of dive in really quick to some code before we get into the rest of this. So we're going to first show you the basic dispose pattern. So this is the most common implementation of idisposable that you will have in your programs. And that pattern is defined as a class that implements idisposable. You'll typically have a private Boolean field called disposed, and this is how you know whether or not you've already freed resources for this class or not. You'll usually have some kind of private object that also implements idisposable, which warranted the need for this. Now in this case, like I said, we're going to use bitmap objects because they're really easy to work with. So we're going to take one in as a constructor parameter and store it as a private field. So the two key parts to the basic dispose pattern are A, the public dispose method with a call to dispose true, and GC suppress finalize. Dispose true is indicating that the dispose method was called from user code, meaning that somewhere in your program you wrapped this class in a using statement or you called dispose directly. If dispose is called with false, that typically means that the garbage collector called dispose because your class implements a finalizer and gives your class that last opportunity to do some cleanup. And then in this case, because we're calling dispose from user code and we're freeing our unmanaged memory, we can suppress that finalizer because there's no reason for it to run. Part B is the actual protected member dispose, which is overridable in a non-sealed class. That is important. With that parameter, we're going to do a check to see if the object has already been disposed of. This is critical to ensuring that calling dispose is safe to call it multiple times and that it also has no side effects. If the object has never been disposed and it's the first time, then we're basically going to do a check to see, is this being called from user code, which means that it's safe to reference other objects at this point in the scope and call their dispose methods. This would not be valid to have this outside of here, because then what could happen is this method may have been called by a finalizer, and this object may have already been finalized, and we can't guarantee if it has been or hasn't been. And so we need to guarantee that this is only being disposed of by user code. And then finally, we basically say that our object is disposed of at the end of the day. So this is the most common pattern, basic dispose pattern. It'll pretty much look like this 90% of the time. I did put these debug statements in here because we'll show you what the program looks like here in a second. So the program, let's take a look at what this does. It's just a little console app that demonstrates the various patterns I'm going to show you today. So we're going to demonstrate a memory leak. I'm going to show you deterministic disposal, indeterministic disposal. Both of those are using the basic dispose pattern, but they're different behaviors of that. I'm going to show you a class implementation that provides a finalizer and how that behaves. And I'm also going to show you how implementing the idisposable pattern when using inheritance works. And then finally, there's a couple commands. We're going to force garbage collection because we need to do that to demonstrate some of this. So let's just run, for example, our basic deterministic strategy. And so what happens here is in our strategy, if we go, strategy pattern is what I'm using for this program. So we have a basic strategy. All this really does is we're not storing any of these. We're going to create these instances of bitmap image, as I showed you where we implemented the pattern. But all we're doing is we're creating 10 of these in a for loop. at the end of the day. And we're not holding references to this variable anywhere in the program except for within the local scope of the run method. And so when the run method goes completes, none of these variables will be in scope. And actually, as soon as the loop iterates, each instance of these will no longer be in scope. And so the point of that is the garbage collector in a .NET application is a reference counted garbage collector. And so what that means is the garbage collector tracks the number of references to any given object throughout your program. And only when the number of references to that object is 0 can that object be eligible for garbage collection. Now, just because the reference count is 0 doesn't mean it will be collected, but it will be eligible for collection. And so if I were to store this in a list, like a static list or something, there would be one reference, two references within the for loop. There would be the variable reference, and then there would be a reference that the list has to my variable, but we don't have that in this case. When I demonstrate the memory leak, in this case we have a static list, and in this case we will be holding a reference to our bitmap image. And so that, just understanding reference counting in terms of garbage collection is important, because if you're expecting an object to be freed implicitly because you're not calling dispose, but the memory is not being freed, it's probably because there's references being held somewhere in your application. But there's also behaviors, even if the reference count is 0, it doesn't necessarily mean your object will be disposed unless you're calling it explicitly. And so in this example, I've provided what I call deterministic disposal and indeterministic disposal. And so let's show you what those things do. So in this case, I ran the deterministic strategy. And like I said, all this does is create these images in a for loop and call the dispose method. And so in this case, it does free the unmanaged memory that's being held by the bitmap immediately, which is what we would typically expect when we call the dispose method. Now, if I were to call the indeterministic method, what we're going to see is that the memory is not freed. So here we can see that every iteration of the loop, we lost about 50 megabytes of RAM. And ultimately, none of the memory was ever freed. So all that happened was the amount of memory being utilized was increased. And if we go look at that, again, it's the same strategy. The only difference is in this case, we're not calling the dispose method. Well, you might expect the garbage collector to free this memory, but again, this is unmanaged memory, and the garbage collector does not know how to do that unless you, the developer, call dispose to make that happen, or there's a finalizer implemented to guarantee it can happen. And we'll talk about that here in a second. So in this case, we did not call dispose. We basically have a memory leak. The difference is between a true memory leak where the reference count is greater than 0. In this case, we have a reference count of 0. So I can actually force the garbage collector to run, and in this case, it will free all of that allocated memory. Because again, there were no references to any of these bitmap images after the method completed. So it's indeterministic because there's no guaranteeing when the garbage collector will free this memory. So let's talk about that for a second. So if we go here, deterministic. So again, you're basically calling the dispose method directly. The reference count does not have to be 0 for you to do this. It's safe to call dispose, but that is one of the reasons why it's important to make your dispose method safe to call multiple times, because it may have been disposed of and you don't want multiple calls to crash a program. However, it is good practice that if you have properties or methods on your class that should not work after those resources have been freed, you should make sure you do that check based on that private disposed field, true or false, and throw an object disposed exception. So the other aspect of this is that, again, we're talking about freeing unmanaged memory. So the managed memory that was allocated by creating the new object itself, if the reference count is greater than 0, while the unmanaged resources would be freed, the managed memory that was allocated for that object might not be because the reference count is greater than 0. And then again, finalization of the object is suppressed because we freed the memory directly. There's no reason for the finalizer to run and freeing those unmanaged resources directly. So you're probably wondering in this sample, where are the unmanaged resources? All we have so far is a managed bitmap image object with a managed bitmap object loaded from a file, and we're calling dispose. There's no native code in here. You as the developer, it's important that when you're using any library like .NET itself or third-party libraries, you have to identify the objects that you're using if they do implement idisposable or not. So in this case, the bitmap class does. And it derives from image, which implements idisposable. And at some point in the image class, we'll show you it creates a native bitmap object using the GDI plus APIs. And so if we were to look at this chain of events, what's happening here is when we call dispose on the bitmap image, that calls our dispose method with a true parameter, meaning it was called from user code, which in turn calls dispose on the underlying bitmap, which then calls the dispose with the true parameter for the bitmap, and finally calls GDI plus dispose image. And so this is a platform invoke function that's defined in GDI plus.dll, I believe. The native resources are actually created if we were to decompile the image class from file and dive all the way down. This is where you'll be able to find that it actually creates the native memory and a handle to that in code. So if we go down here, we have GDI plus load image from file. This is where it actually creates and allocates the unmanaged memory. And so this is, as long as you identify that an object you're using implements idisposable, it's safe to say that it's implemented because they're holding on to unmanaged resources. And this is just one example of how those could be allocated. And so if we go back, dive down to the image destructor or the finalizer, we can see that it implements dispose and calls false. And this is where it calls dispose image. So again, we're only freeing unmanaged memory at this point in time. So here we can see bitmap image dispose. I've just kind of broken this down, basic dispose pattern. And then ultimately, when we call dispose on the bitmap dispose, and GDI dispose image. So pretty straightforward. So that is deterministic disposal, as I call it. Indeterministic is a little bit different. So this means that you forgot to write the code to wrap a bitmap image or class in a using statement, or you did not call the dispose method directly. And so what happens here is for your unmanaged memory to be freed, the reference count would need to be 0, and the finalizer of the bitmap object in this case would need to run. And so, because in our basic dispose pattern, we did not provide a finalizer, so we didn't provide any mechanism for the garbage collector to call into and say, I'm going to give you a last chance to clean up native resources. However, because the bitmap image in our loop here goes out of scope and the reference count becomes 0 outside of the loop, in turn, the reference count for bitmap also becomes 0. And because the bitmap image itself implements a finalizer, that will run, and that will allow the unmanaged memory to be freed, even if you do not call the dispose method. But there's gotchas. So typically this will only happen if you actually allocate enough managed memory to create enough memory pressure for the garbage collector to actually say, hey, I need to run and I need to try and free up memory. And so typically you'll actually run out of memory, unmanaged memory, before this can ever happen, and you'll get an out of memory exception. But if you're lucky enough and you do have a lot of managed memory being allocated and the garbage collector says, hey, I'm going to schedule your finalizer, it'll basically take that bitmap finalizer and it will put it on the finalization thread in a queue. And when that finalizer is removed from the queue, it will execute. And at that point, the bitmap will have the opportunity to free the unmanaged memory when that finalizer is executed. Problem is, you should consider this a memory leak because it's indeterministic, because there's no knowing exactly when this will happen in your program. The garbage collector implements algorithms that determine when it's appropriate to do all this work, and there's different behaviors in the garbage collector, but ultimately knowing that the reference count has to be 0 and there has to be enough managed memory pressure is very difficult, and there may never be enough managed memory pressure. So ultimately it should be considered a leak. So let's actually demonstrate that. So if we actually were to run again our indeterministic strategy, right, we're not calling dispose, but because we're not holding any references, when the garbage collector decides to run, and it hasn't yet, I can run this strategy twice, and you'll see that all that's happened is more memory has been allocated. Nothing has been freed. And that's because, yes, we're allocating a lot of memory, but we're allocating a lot of unmanaged memory. We're not allocating enough managed memory for this to fire. So, but because reference count 0, if I force garbage collection, all of that memory is eligible for collection. I can get those finalizers, in this case now ran the finalizers for the bitmap object. So when I called that GC method, if we go back down here, what happened was I forced the garbage collector to run. The reference count was 0. In this case, memory pressure doesn't matter because I forced the garbage collector to run. The finalizer of the bitmap object got scheduled for finalization. It got removed from the finalizer queue, and then it executes. And then when that executes, ultimately it will call the dispose method in the bitmap with a false parameter, and ultimately GDI plus dispose image gets called. So very important to ensure that you as a developer are always wrapping these and using statements or calling dispose directly. Otherwise, regardless if you want to depend on the garbage collector to at some point do this, there's no guarantee. So it should, for all purposes, be considered a memory leak. So we've talked about deterministic and indeterministic, but there's also what if we provide a finalizer. And so, right now what we've done is we've implemented the basic dispose pattern and just really demonstrated the two different behaviors. But now I'm going to show you how to implement a finalizer correctly and why you would implement a finalizer. So first off, just like in the system.drawing.bitmap class, how it actually does direct creation of unmanaged memory using platform invoking, if you're going to do something similar, or you're going to use the Marshall alloc global or use unsafe code, and you are directly going to instantiate or allocate unmanaged memory, then you know that you need to provide a finalizer for your object. If you're never creating unmanaged memory directly, you don't need to provide a finalizer. So in this case, I just provided a different implementation of bitmap image where I've removed the system.drawing.bitmap object in favor of a file name. And what we're going to do is exactly what the bitmap class does. We're going to use the GDI plus platform invoke methods, which really are Win32 methods directly, and we're going to allocate unmanaged memory ourselves. And so in this case, we don't have any managed objects that we're storing references to. So I'm going to implement a finalizer. I'm going to call dispose false. We still provide our dispose method because, again, remember, you really ought to be calling this directly instead of relying on the finalizer. But in this case, we can provide a finalizer, and the pattern is very similar. You still have your if disposed to make sure the method is safe to call. In this case, because we have no managed objects, we don't have a if disposing clause with a dispose call on another object. If we had a mixture of managed objects that implemented idisposable and native memory that we allocated directly, we would have both. But in this case, all we have is just a direct call to dispose the image using platform invoke. And then same thing, we mark it as disposed when we're done. So typically when you're writing unsafe code, native code, or platform invoking, this is when you'd provide a finalizer. So, and really, if I was to add one more thing, it's really just because we're not having to rely on the finalizer of another managed object. So if we now run our finalizer strategy, what you'll see here is, again, we created a bunch of bitmap objects. So here's our finalizer strategy. Some of this code is just when you're creating GDI images directly, you have to do some startup and shutdown code. So don't mind this block here. It's not really relevant to what we're talking about. But we have the same thing. We have a loop. We create 10 iterations of bitmaps. In this case, we're not calling dispose directly, and we do have a finalizer implemented. So in this case, we don't even have to rely on another managed objects finalizer like bitmap, but if we were to now call and force the garbage collector, we can observe that we can free that memory as well. Because again, in this case, the reference count doesn't even matter because we're not talking about a managed object, but we basically forced garbage collection, which scheduled the finalizer on the finalization thread in the queue, got removed, executed, and then freed our unmanaged memory. So the last strategy we're going to show is an actual memory leak. And a memory leak is essentially if you have some unmanaged resources, maybe you have the disposable pattern is implemented correctly, but in your code, you neither call dispose, and even though the bitmap class that's encapsulated by bitmap image has a finalizer, we are storing references to each of these bitmaps in a static collection. And so what we're doing here is we're basically saying the reference count is greater than 0 at any given time. And so just like a memory leak where we could free it, really unlike that, in this case we will not be able to free it. So if I run our leak strategy, again we see that we have a bunch of memory that was allocated, and because we did not call dispose and because the finalizer will run at some unknown point in time, we have a bunch of memory use. Now, if I force garbage collection, I have 0 kilobytes freed because the reference count is greater than 0, and so the finalizers cannot be scheduled on the finalizer queue. Now what I can do is I can clear those references. So I implemented this CLR command, and all that's going to do is clear this images collection and remove the references to each of those bitmap images. So I'm going to run that, and we have 10 references removed. Now the reference count for those variables will be 0, and if I force garbage collection now, I should get my memory freed. And so this is important to understand, that you can leak memory in a variety of ways, but if you leak memory and you have references floating around in your software, it can become very hard for you to ensure that that memory can be freed automatically. And so typically you need to go through your program, and if you have memory leaks today, your bug fixes are typically going to be writing using statements or calling dispose, making sure that ref counts and objects are where they need to be. But if you just write code with all of this in mind from the get-go, you can avoid it quite a bit. So very important to understand how idisposable works. we'll talk about one last thing, which is inheritance. The same concepts apply. The pattern is a little bit different. In this case, I'm not going to show you a finalizer for implemented with inheritance, but it's essentially the same. So the difference is, in this case, we're going to show how do you implement idisposable with a derived class. So let's look at the base class, image base, implements idisposable. You still have your same basic dispose pattern. Nothing different. We have this is a system.drawing.image, implements idisposable. There's our dispose method. There's our pattern, if disposing. There's our managed object, so on and so forth. When you derive from a class that implements idisposable, the important thing is your base class must make this virtual, and you need to provide a similar pattern on your derived class. So you're going to provide your own private variable disposed in the derived class. You should not make your disposed variable in the base class protected. They should be separate. And so in this derived class, now we take a bitmap image and just pass that down to our base constructor. But same basic dispose pattern. The difference will be we're going to dispose of our derived class resources first. We have the same checks to make sure that it's safe to call dispose here, and the same checks in the base class here. But once we're done disposing of our resources in the derived class and mark it as disposed, then we're going to call down to the base class dispose. And that's as simple as it gets for implementing it in inheritance. So you have to make sure that you manage the life cycle of these objects correctly. So that way you don't run into scenarios where, you know, your base class implementation, you know, disposing of something in that last might impact objects here. So you just kind of have to be careful about that, or vice versa. You know, if you dispose something here first, would it impact code in your base class dispose method? But typically not, unless you do something really weird. But just something to keep in mind. So I'm going to include this application in the source code in the description of the video, so you can play with it and hopefully understand a little bit more about the idisposable pattern. Hopefully this video was helpful. Again, I didn't cover a lot of information about how the garbage collector actually works. I could have gotten into how it frees memory for generations 0, 1, and 2, the lifetime of objects. There's configurations for the garbage collector if you want to run in workstation mode or server mode or concurrent mode. The garbage collector is pretty complex, but I guess let's actually add a few last things. Best practices. So number one, never force garbage collection in your program, ever. If you're doing that, you are not implementing idisposable correctly, and you're not managing your memory correctly. You should never have to call gc.collect. You should really never have to configure the garbage collector either, or tweak settings of the garbage collector. So the best rule of thumb that's typically agreed upon by all the best developers I've ever known is do not toy with the garbage collector. Leave it alone. Let it do what it does best, and you focus on implementing idisposable correctly and managing your unmanaged memory correctly. You know, I can't stress that enough. Just leave it alone. You typically don't need to call gc.collect. However, there are times where it is valid to call gc collect. I'm going to emphasize it's rare. But let's take an example. Let's go back to our program here, and I'll give a real use case actually. So in an enterprise application for the banking industry I worked on, one of the major functions of the software is merging documents together, and we're talking 200 to 300 DPI TIFF images. They're compressed to a degree LZW or black and white compression, whatever the bank is scanning in. But these images can be quite large, and so when you store them in memory, it takes up a lot of RAM. And the merge function, when you're merging documents together, you need to merge, you're basically adding pages of a document to another. And it needs to happen as quickly as possible, but because that you might have one of the pages in memory at a time. And what happens is, in that case, the garbage collector will typically run, and you can see the memory fluctuating up and then down as the garbage collector runs. Or you can see the garbage collector allocate a bunch of memory, and then when you're done merging all the pages, you'll see it jump way up, and then let's say you're done merging 10 pages, it'll jump way back down. Well, there are times like that where when you're done, the garbage collector might decide that, hey, I'm not going to free a bunch of memory when you're done because maybe I'm going to keep it around in the process. Just because your application has a lot of memory usage doesn't mean it's a bad thing. It might be freed at a later time by the garbage collector. It just might not happen exactly when you expect it to, especially in the case of managed memory. So, there are times where if you perform a large operation like that, and when you're done, that you know a little bit better than the garbage collector, and you can call GC collect and get the memory freed sooner than later. But in my experience, even then, if you just leave it alone and you implement idisposable correctly, you can pretty much avoid that. So I kind of lean towards the spoken rule of just leave the garbage collector alone. You would have to really, really convince me, with the piece of code that it's valid to call GC collect. There are places in the .NET framework where Microsoft calls GC collect. Just because they do it or you see someone else do it doesn't mean it's the right thing to do. So don't interfere with the garbage collector. All right, well, I will attach the deck of slides here and the source code to I'll upload them to my OneDrive and put those in the description box of the YouTube video. If you found this helpful, share the video, give it a thumbs up. I want to get some more traffic to the YouTube channel. I want to keep doing more of these videos. And if you have questions, please ask them. It's memory management, even though it's automatic, there's a lot more to it than that in the runtime. And it's a very large subject as well, especially the garbage collector by itself. And if there's one way to get developers to argue with one another on Stack Overflow, it's to ask questions about the garbage collector. So just ask questions. I'll be more than happy to answer them to the best of my ability. Disclaimer, I don't think I'm an expert on the garbage collector, but I'll try my best. So thank you very much for watching. If you enjoyed the video, again, thumbs up, share the video, and we'll see you next time.